as Jeff said, he said, okay, well, you've done, what did you say? You've used energy. Yeah, okay, so you've used energy, or we say we did some work. Now, actually, work is a change in energy, too. So it's kind of like you can't use the word work without using the word energy, okay? So there's two types of energy. We've already talked about them before. First, we need to talk about mechanical energy. So you have this definition already in your notes, right? Mechanical energy is the energy which is possessed by an object due to its motion or its position. Mechanical energy can be either kinetic or potential. And actually, mechanical energy, we'll represent it with E little m, mechanical energy, is actually equal to EK, which is kinetic, plus EP, which is potential. Now, we'll do this more in Physics 20, but so like a pen, maybe I won't tell you about it yet. I just do it? Okay, so if you have a pendulum, when it swings up, it stops, right? So if you have a pendulum, like a swinging pendulum, actually I hang it from the roof there. I put a mass on that roof, and then we make a giant pendulum. We'll do that after, okay? Anyways, so when a pendulum is down here, it has, like in its swinging and down at the bottom of the swing, you don't have to write this down, you can just listen. It has all kinetic energy, it's moving really fast. But then when it swings to the top, right at that split second before it comes back down, it doesn't have any motion, right? So all at the top is all EP, because this has potential to go do work once it comes back down. So a pendulum is a good example of how mechanical energy can change. Here, the pendulum is all kinetic energy. Here, it's all potential energy.
So it's using energy to go back.
Back and forth, yeah. So again, like I said, we do that in Physics 20. So I'll leave that thought with you for now. But anyways, so what is kinetic energy, really? This is the energy of motion. So write that down beside kinetic energy. The energy of motion. So when you think kinetic, think moving. Kinetic. Just kind of like from the kinetic molecular theory when we talked about particles moving, the thermal energy thing. And then potential energy is stored energy. Stored energy. So you store it up. And then put a semicolon. And say energy having the potential for doing work. Sorry, that was kind of fast. Energy having the potential for doing work. So remember this example that we did? Right? We did this example with the elastic band. Okay, Josh? So why is that scary? Whoa! I didn't mean to do that. Okay, so why did that happen, Jeff? What was happening here?
Energy was storing up.
The energy was stored. This is elastic potential energy. And then when it was released, the rubber band was moving, right? So then it was transferred into kinetic. So we remember that kind of stuff, right? We've already talked about that? Okay. So now that we've talked about energy, let's talk about work. So when we talk about work, this is when an object possesses mechanical energy. An object which possesses mechanical energy is able to do work. Possesses is a weird word. Has a lot of S's and E's in it, hey? Okay. In fact, mechanical energy is often defined as the ability to do work. So, the definition then of work is the transfer of mechanical energy from one object to another. So when Arvine and I moved the table, we were transferring our mechanical energy in us, where we're an object, into the table, and we moved the table, yeah? So, and another example, if you stretch or compress a spring, you do work on the spring and transfer energy, or you do work on an elastic, or you do work on anything, okay? The amount of work done on an object can be calculated by multiplying the force, okay, so we're looking at force exerted on the object by the distance which the object moves. So the force and the distance is what we're looking at. So when we think about a force is anything that gives a push or a pull on an object. So force is push or pull on an object. Now let's take out our formula sheets, our data sheets. So, we've done the first one, V equals D over T, on this side of your formula sheet. We did the second one, V arrow equals D arrow over T. We did A arrow equals D arrow over T. Then there's this one that says F net equals M times A, then F net equals F A, F. We're not going to do that. The next one you see there, so the 1, 2, 3, 4, 5, 6th one down, says W equals F times delta D. Highlight or circle that one. W equals...
Is delta like a sideways triangle?
Yeah, the triangle stands for change. So whenever you see that, that means change in. So that just means change in distance. And then look at the side. It tells you what is what and what units everything is. So sometimes I heard some of you say yesterday you were confused about what units time is in or what units acceleration is in. You can look on here and it tells you, right, if you get mixed up. So look here, it says work. So look at the W equals work. It says it's either Newton meters or joules. We can see the force, the F with an arrow. So that means F is a vector. F with an arrow is kilograms times meters per second squared, or newtons. We usually talk about it. And then you can see, and then D is distance like normal. So those are our new formulas, or our new formula. So this is our formula, where W, this means the work, and it's done in, oops, sorry, just pressed too many times. So the work is measured, we say, is done in joules. And energy is also measured in joules, so work is like energy. So we can almost think about them like they're the same word. Force is measured in newtons. And delta D means change in D is measured in meters. So fill in those little lines there that you have. So if you get a question and you're given like the distance in centimeters, what do you think you have to do?
Convert it.
You have to convert it to meters. So these are the only units that you're allowed to have in your formulas. Okay?
For Newtons and joules, is it always gonna be those ones that are given to us, but we're not gonna have to convert it?
You might be given something like kilojoules, and you have to convert kilojoules to joules, but all you gotta do is look at your conversion sheet and look at the kilo and see how much you change it by. And if we do have a question like that, I can work through how to do that type of example then. I don't think I have any like that though. Okay, so in order for work to be done, the direction of the force and the direction of the motion must be parallel or along the same line. So basically, if Arvine and I wanted to move the table from there to there, we needed to do the force, we needed to apply a force to the table in that direction. Make sense? Like if you want to do work to move the table from here to here, you have to apply a force that goes from here to here. That's all that's saying. Okay? It needs to go in the same direction. So those two lines, it's just, don't worry about it, nothing there. All right, let's do an example problem.